the last lecture. We're going to do the Chapter 8, the last module for the CISSP, and I'm not going to have any new material next time. I'll just answer questions, and then it comes to the final. So we're about to the end here. So let's look at software development security. Make this thing get bigger. There we go. All right. So first you have to understand programming. So machine code is what actually runs on your machine. It is binary language running the CPU. It has binary inputs coming in the pins and transistors that process it. That's the only language that it's ever actually used on your computer to run things. But humans don't like writing in that language, so you write in other languages which are converted to machine code. Assembly language is the lowest level language that is almost the same as machine code, but it has readable commands like add, subtract, and push. Each one of those turns into one machine language instruction. Yet that's also very difficult for humans to write. They prefer high-level languages like C, and Java, and Python, and things like that, source code in a higher-level language. So a compiler is what translates source code into machine code. Interpreters translate each line one by one while the program runs, so they are slower but more responsive to user input and useful for interactive things. And bytecode is what Java uses and the .NET framework, where you compile original source code in a high-level language like Visual Basic or C#, C++, and you compile it, but you do not compile it to machine code. You compile it down to an intermediate form, which Microsoft calls intermediate language and Java calls bytecode, and then you run that in a virtual machine. So you can run it on multiple hardware platforms. So you could run a Java program on a Mac, on a Linux machine, or on a PC, all from the same source code, because it's not really compiled to machine code. It's compiled down to bytecode, and then on whatever your machine you're using, you have to run a Java virtual machine, which takes that bytecode and processes it as the machine language appropriate to that hardware. So that's another way to do it. All right. The end result of this, by the way, in practice for reverse engineers, is if you use one of these things like Java or .NET, you are effectively handing your source code out with the application you give the end user, because that intermediate language is easily reversed back to the high-level language. If you use C or another language that's compiled all the way to machine code, the compiled version is not closely related to the source code, and reverse engineering it is difficult using tools like IDA Pro and such, and Ghidra these days. All right, so procedural languages are the original early ones. They have subroutines, procedures, and functions like C and Fortran. Then object-oriented languages came by much later, where you define an abstract object, which is a data structure, which may have multiple data and it may have attributes and methods. You define a object, and then you can define subobjects. You can define an object called employee, and then you could have an object called managers, which is a subset of which is based on employee, so it inherits all the employees method, like pay and sick leave and stuff, but it adds extra methods, like promote people, change their pay, and things like that. And this is what the more advanced languages have, more modern ones, C++, Ruby, and Python, are object-oriented. Metasploit is written in Ruby, at least it was, I think, when I wrote this, and it's object-oriented. So you have a class Metasploit, which has this : it's at some container called MSF, and then exploit, and then remote. For this one, HTTP client. So it has, there's some kind of indicator of containing. So inside the class Metasploit is a container called exploit. Inside that exploit is an object called remote, and this is an object called HTTP client, which is based on remote, which is a child of remote, and remote's parent is exploit, and this parent is MSF. That's how you do it. You organize things into a parent-child relationship in object-oriented languages.
Those are classes.
Yeah, they're classes. I think it's the same thing, but maybe it's different. I'm not that good at this. I never did do much object-oriented programming. I only know the general terms.
I think it probably means something else.
You could be right. It's anyway. So then there's something called fourth-generation code, which is where we're all headed. And the thing that's not here yet, because I don't think it's on the CISSP exam, of course, is now people are going to automatically generate code with machine learning. That's big. But anyway, so the fourth-generation languages are these object-oriented ones. And I really mostly use the third-generation languages. I use object-oriented languages, but only in a very simple way without really exploiting their object properties. By the way, PowerShell is fully object-oriented. And to understand how to use it very well, you really have to get comfortable with the object. The output of a PowerShell command is an object, and you pass it into another object. I'm pretty clumsy at that. I use it like the old third generation stuff. So I'm glad you point out that I probably might not be getting it right. I very well might not be getting it right. I never really got very good at this fourth generation stuff. All my coding is third generation. Anyway, so here's a program to assist in creation and maintenance of programs, some tools. Tools support one task, workbenches integrate tools, and there are environments that support the entire process. Like a lot of people are Microsoft oriented and they want to use Visual Studio for everything. That's their environment. And like I say, I don't use it much. I typically use just a text editor to write one program, and that's the old-fashioned C Fortran technique. Modern technique uses a coding platform, an environment you live in. All right, so top-down is where you start with high-level requirements, and then you write code to achieve that. But there's also bottom-up where you start with low-level details and move up from the bottom. So closed source like Microsoft Office and Windows is confidential. You do not have the source code. It's a guarded secret, so you can run it, but you can't really modify it very well. Open source is the alternative, like Linux. The code is completely available. You can read it, you can analyze it, you can look for security flaws in it, you can modify it and make your own version. Some software is free, some costs nothing. It has limits to how it can be shared. There's trial periods, and there's ones that limited free versions. All right. Then this is connected to licensing. Public domain software is free to use, free to copy. Proprietary software is copyrighted, and they'll prosecute you if you make unauthorized copies, or at least they can. There's an end-user license agreement limiting what you can do with it. And there's a whole bunch of open-source licenses, like the GNU Public License and Berkeley Software Distribution License and the Apache License, various licenses that have different restrictions on what you can do with open-source software. One interesting example is Donald Trump's Truth Social. Donald Trump's Truth Social is Mastodon. The early versions didn't even bother to cover up the Mastodon logo or anything, and Mastodon is open source software, and there was an argument at that time that they were violating the license, but I didn't hear of any actual legal case coming out of it. Anyway, so to develop your application, the original old-fashioned model from the 60s was waterfall. You'd do the first step, then the next step, then the next step, so you'd have your requirements, then your system requirements, software requirements, analysis, program design, coding, testing, operations. The idea was just have a series of steps like an assembly line. You do your job, pass it on to the next group, and they would do their job and pass it on. And this is totally unrealistic. In practice, it never works. You make a design decision, you pass it on, and then somewhere later they decide, wait a minute, that design decision led to a disaster, a conflict with another problem, a security problem. You have to go back and fix it. So this waterfall model is not useful, really, for complicated things like coding. So they have this one where there's some way to go back and say, wait, no, this is not appropriate. You have to go back and redo this step. This is what actually happens. You have to keep going back. And then there's one with the sashimi where they overlap. So you do one step, and then you work with this team to work on the next step and the next step, because that's a problem. You can't actually do something and say it's done and not have to reconsider that, because the other teams may well find flaws that require you to rework things. Then there's Agile. Agile tries to not hold your team back with a bunch of burden and requirements, but just let them go fast. So you try to have individuals over processes and tools and customer collaboration as opposed to contract negotiation. This is, I think, what Facebook focuses on. Facebook actually has written on the wall, move fast and break things. They named their building Hacker Building and named the street Hacker Way. They just want everyone to rapidly make things and have fun doing it and not worry about rules and compliance frameworks and restrictions and change control boards. They don't bother with any of that. You write anything you want, and they push it out to a small number of users in like one area, and then they wait to see if it works. And if it works, they just roll it out more. Scrum is another way to do it, where instead of having a project, it goes to one team and then another team and another team, where very frequently the third or fourth one will decide, wait, there's a mistake, send it back to those other guys. You make one team take it through every stage of the process, which is a rugby move, where Scrum runs all the way through. I must say I like this because the companies I worked at, if you read a book called The Phoenix Project, it explains very much how this works. It's very good. And it explains every company I've worked at. And one thing I found at every company I worked at is most people would solve their problems by just making a problem for some other team. You would send it back and blame somebody else, or you'd do something that you knew would make trouble later, but that's how you'd move things off your desk, was just do something the whole point of the DevOps process, which is explained in that book, is that you prevent that. You have the management watches, and anytime anything goes back for rework, they focus on that and make sure it won't happen again and automate that so it won't happen again to make sure things flow smoothly through. And the king of this is Amazon. Amazon has 144,000 rollouts of new code per day. They do not have a lengthy process of checking. It's all automated. If you make a change, it goes through a series of tests, but it's all automated. So most of the time it goes right through to the end, like a machine. So the Amazon website is not a fixed thing with like version 1 and then after a month version 2. It is like a living organism. It's constantly changing. There's a code constantly flowing from all the developers changing it. And tests to see if that worked, and then revisions passing through, which is what you get with DevOps, the complete automation of these things. So extreme programming is another agile technique where you have pairs of programmers that work off specifications and they work together. Pair programming is quite common. Two people can work together. Hopefully they will notice flaws if two people work together is the idea. And then there's spiral, where you just have many rounds. So instead of having a beginning to the finish, this is probably the most realistic. You begin it, you have a risk analysis, you make a prototype, then you go back and have another development, try re-engineering it, then you make another risk analysis, another prototype, then you have another risk analysis, and another prototype. This is probably what you really do. If you have a product like Windows, it's never done. You're just constantly revising it. It's just growing bigger and bigger like a snail. This is probably a more realistic description of what happens with big projects. All right, then rapid application development. You have prototypes and dummy GUIs so you can show the customer. This is what web application developers often do. They sort of draw a sketch. Okay, it could look like this and have a button here that does that, and then you see if they like it. Prototyping is essential in almost all of these, where instead of working hard to make a perfected end product, you make a quick product that approximately does what you need so you can show it to people and test it and see if it's accomplishing your goal before you waste a lot of time making a finished product. You make a mock-up. The software development lifecycle is very important. Microsoft uses it a lot. It's also defined in a NIST standard, 814, and this is where you have security review in every phase of development. So you have initiation, development, and acquisition of resources, then implementation, operation, and disposal, and you have security considerations at each level. So you make a plan, you define the purpose of your software, and then determine how sensitive it is, what kind of data it handles, and whether that is a risk. And then you get your requirements, incorporate them into specifications, you implement things, and then you operate and maintain it with updates and all that jazz, audits and monitoring, and then you dispose it somehow. When you're done with it, you have to archive whatever you want to keep of it, and you have to sanitize your media and destroy whatever you don't want to keep of it so it isn't just leaking out. So, all right, you got these integrated product teams. Another way to do it, a customer-focused group to try to keep things on track. And software escrow is another issue. Sometimes you build your business on an all-essential product and you don't want to know that that company might go broke and the product might be gone. And so you might have the source code of that placed somewhere so you can get it if they go broke. Also, there is a law I've heard of, which I've seen people use, where it is legal to reverse engineer something if the company no longer exists and you need it. Otherwise, it's illegal to reverse engineer something and figure out how it works and make a clone of it, although it happens all the time. All right. So there's code repositories, big issue, like GitHub is the main one. You put up your code so you can keep track of versions and so you can share it with other members of your team, but a lot of people put public things in GitHub that shouldn't be public. And like they have something like hard-coded credentials in their source code and so on. And there's increasing levels of GitHub security. They've added more and more products to GitHub to notice if you're putting things in there that probably shouldn't be public. And then there's APIs. APIs are a big issue. That's probably the number one web application security flaw these days. You have a software program running on a server, and it takes requests from other servers with an application programming interface like Facebook. Facebook has its own internal structure where users can log in and they can put up things on their wall, but it also lets third-party products connect to it with an API. Third-party product can use Facebook for a login, saying, I'm a different product, but people want to log in with Facebook, so it sends requests to Facebook, Facebook collects their credentials, and then it sends a reply back telling Facebook, okay, this person logged in, and you're authorized to see their name and address, but nothing else. And that's what APIs do. They offer some functionality to external entities that come in as web requests. And very, very often, those functions do not correctly handle authentication and authorization. So there are APIs that let you make a call to receive data that you're not supposed to have. That's probably the number one flaw currently in web apps. I see some comments from Shu here. In 2000, someone told me the number of good C language programmers was pretty limited. Oh, I imagine that's true, depending on levels. I mean, you have programmers at different levels. There's these ones they call the 10x programmers. There are programmers that say they're worth 10 times other programmers. And I imagine that's true. A lot of people are sort of careless and sloppy. Some people are real experts. Tencent moved all the C and C++ programmers out of the QQ Desktop Software Development Group and investment firm to other departments. All right. Yep. Anyway, people are constantly struggling with this. And by the way, I've heard that the highest paid job in tech is developer, more than security, more than anything, because you're right in creating the thing that they really need. So good developers, they say, get paid really a lot. Anyway, so there's OWASP lists considerations for API. These are API securities. You have to consider authentication, making sure you know who's coming in, access control to see if they're allowed to do what they're trying to do, input validation and output escaping, cryptography error handling, HTTP security and configurations, the sort of thing. These are many of the considerations you have to put on your API, and in practice, they're often not done correctly. Then, of course, changing configuration management, the stuff that they sort of hate, as far as I can tell, at Facebook, where you make a proposal and it goes to a change control board to decide if this is really a good idea, if this will have bad consequences. And this frustrates developers because you have an idea and you're not allowed to do it. You have to wait while some sort of irritating bureaucrats argue about it for weeks and then say no, and you don't get to have fun. Anyway, they describe how they do it in their document, configuration management plan, change control board, and so on. DevOps. And by the way, I know this Microsoft is the opposite. I read a blog from a guy that worked at Google and worked at Microsoft and left, and he said he was supposed to design the shutdown menu for like Windows 7, where you click on the little arrow and it says shut down, sleep, hibernate, or whatever it has, like 4 or 5 options, log off. And he said, we made that menu with like 5 items, and I spent an entire year, they kept changing that menu. No, give it 4 items. No, give it 3 items. He said, the whole team spent a whole year working on that stupid little menu until I just quit. I said, this is insane. And that's what happens in these bureaucracies with all these layers. Some trivial little detail becomes nearly impossible to get through the approval process. Anyway, so DevOps, as I mentioned, is the newer system, more agile, where you find all the places where people are getting frustrated and wasting time and undoing each other's work, and you carefully remove all those. And you make sure that everybody at every stage is a programmer that can automate whatever their task is, so that most of the time, software from the developer just flows loop, 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 loop right through the chain and reaches the end user right away with no friction. That's what Amazon has going. And it's a big, that way everybody is happier and the product is better, but it takes a whole different philosophy of management and a whole different philosophy of staffing and different expectations on the people. So, like I say, there's a very good book about it called The Phoenix Project. Very interesting. Anyway, let's take a look at a Kahoot. All right. I thought it's kind of funny you mentioned that because I've, every time I'm doing, what is this garbage? Wait a minute. Already have an account. Thank you. Oh, good. Anyway, every time I'm writing coding challenges and stuff in Python, I'm reminded of the fact that I'm not really doing it right. I write Python like it was COBOL or Fortran. And theoretically, there's all these modern ways to do it, but I've never gotten good at them. So there's a thing called Pythonic. Is your code Pythonic? And my code is never Pythonic. It's using Python in the old-fashioned way, without using the advanced object-oriented features, which I can never understand.
After all, a program language also has default mode to be regular procedure mode.
Has what?
Object-oriented programming compiler normally has a default mode.
A default mode.
Yeah, for the regular procedure type.
Okay, yeah. Oh, fair enough. I mean, I know I can write procedure type code in Python. It works. It's just I have things like loops when the cool people just have one reference to an object that somehow automatically applies to the whole object. Now, using loops is pretty much a sign that you don't really understand what you're doing in Python. I find Python very useful, but I'm by no ways means a master programmer. I did a coding challenge one time where you had to write something and then you had to make it really fast. And I could make it work, but I couldn't make it really fast because you actually have to know real computer science quality programming to do that, and I don't. I only know enough to make sort of prototypes. Of course, I could use ChatGPT to write it. That would probably do it. All right. All right, so which code has commands like add and push? That's assembly language. Good, all right. The machine code is the binary expression of that, but it's just binary. The add and push is something added for humans to understand it. That's the difference between assembly language and machine code. All right, so which method has no process for redoing a previous step? Yeah, that's waterfall. The old model, which might work for assembling a car on a line, but in practice it's not complicated enough for software development. All right, so which one of these is agile? All right, that's XP. All right, so which technology lets some apps use your service, like apps from other companies? That's an API. All right. All right. Good. All right, let's go back to here. So, then databases, something I'm much more comfortable with. So, there's a structured collection of data. You could just store data in a file, but if you have an organized structure, it's better. So you have like an address list, account numbers, dollar amounts, and things like that. So then you have queries. You can search for data, you can insert data, you can delete data, and you have a database management system which runs this. The database administrator is the user that is able to make changes to the database. They typically use a structured query language, and there are various attacks. An inference attack is a way to find secrets by enumerating low privilege data to find missing items, which must be high privilege. This is what happened in the movie War Games. They made an auto-dialer that would dial all the phone numbers looking for the special ones that reached computers. An aggregation attack is where you combine many low-privileged records to deduce high-privileged data, which may be more complicated than this, where you're just looking for the missing items. You're somehow accumulating information from low data. All right. I know one example of that I heard was that they said you could detect when the Pentagon was doing major troop movements by seeing how many people ordered pizza. Because when they made their staff stay late, they would buy pizza. So there's more pizzas bought at the stores near the Pentagon when they're making military maneuvers. So that's a low privilege bit of information that can be used to deduce a high privilege bit of information. So relational databases are the most common. Then there's hierarchical, object-oriented, and flat file. are other types. This is a typical relational database. You'll have like a users that has a username and field whether it's the administrator, and then a table containing social security numbers with a common field, username that matches, and then social security number. So you can have a link between these two tables on the unique identifier, which here could be name, although in practice you don't normally use a name because names are not unique enough. Two people might have the same name and people might get married and change their name. So typically you assign them like a user ID number, which will not change, rather than using something like their name. But you have flat files and you connect them with a join, and that's the relational database. That's why they call it that way. You have tables that are related to other tables. So tables have rows, and each row contains columns, which are fields. The primary key is the unique number, like a social security number or a customer ID number. A foreign key is a field in another table that matches a key in your existing table so it can be connected. And a join is what connects two tables by that field. The most common one, by the way, is like the typical example is customers and orders. You have a list of customers, but each customer might order many products and they might come back another day and order even more. So you will have many orders in the orders table that all map to one customer. So if the customer does something like change an address, you change it just in the customers table. You don't put something like the address in the orders table where you would need many copies of the same information. Anyway, so then there's integrity. Integrity makes sure that your database does not have a defective structure that makes no sense. Like if you were to have a duplicate in the key field, that would make no sense because it's supposed to uniquely identify records. And if the key that is supposed to match the key in another table doesn't match, then that would again break the join. So semantic integrity is another one to make sure that the data stored in each column is the right type. So if you have a numerical field, you can't have letters in that column. And entity integrity is another one, make sure each object, each row in your database has to have a non-null primary key and a non-duplicated primary key to uniquely identify that row. So here's a table lacking integrity. The primary key here is social security number. They have two records with the same social security number, so that's a violation of integrity for the key field. And here's another integrity failure. You have sick time, but then you have a Nexus 6 here, which is not a measure of time. So that's the sort of thing. Those are violations of integrity. Database normalization is where you remove duplication of data. Like I said, if you were to put the address in every purchase a customer made, you'd have many, many records of the address, and that would mean when you tried to update the address, you wouldn't get them all. And so normalization is arranging your database so it doesn't have any extra copies of data. It just has one place for every bit of data, and you can make sure it's correct in that one place and it's connected correctly to all the other tables. All right. Then you have a user interface, lets you see what's in a database. So if you go to McDonald's and buy hamburgers, the checkout person has a screen that says you could have hamburger or fries or these other products. There's a whole database behind that with all their products and all the customers and credit card numbers and everything, but they have a view that shows them just a select amount of data. And the same thing's true if you log into Gmail. You see your mail or your profile with your picture. It doesn't show you anybody else's stuff. That's a database view, which lets you see a limited amount of the data and control it. You don't see all the other data that you're not supposed to be messing with. The administrator, of course, can see it all, and they have a more complicated interface. But the view is supposed to show the user a simple, clean interface with just a few things on it so they can do their job, like being a cashier, without having to know the internal workings of the database. A data dictionary describes the tables. The metadata is the data about the data, like the list of all the tables and all the fields and columns and data types and so on, and that's called the database schema. So here's a schema. You have employees that have name, SSN, and title, and you have formats for that data, and then you have an HR table with sick time and vacation time, and you have the primary key of social security number to connect to this social security number. This is the way everybody did it until about 15 years ago when the U.S. government started enforcing a rule that private businesses are not allowed to use the Social Security number, but only the government. And so that's why you have a student number at the college and a Safeway number at Safeway and everybody. Every company has to assign you its own unique number. They can't be using your Social Security number or they'll get punished by the government. So you control it with query languages. There's data definition languages and data manipulation languages. Typically you use SQL, structured query language, and there's many different versions, the Microsoft version, the open source version, Oracle version, and so on. All do pretty much the same thing. So you create a table, select a record, delete a record, insert a record, or update a record, and have things like this. Select all the data from employees where title equals detective. This sort of thing is what SQL queries look like. Now, a hierarchical database is a different structure. Instead of having a master table, which might be duplicated on redundant servers for performance or fault tolerance, you have a whole connected bunch of servers that each contain a different amount of data. So in DNS, you have a root, and the root of DNS just has information of where the top-level domains are, which there used to be only 13. Like .com, all it has is where these top-level domains are. So if you want to find like www.google.com, first you go to to find out where the .coms are, then you go to .com to find out where google.com is, and then it tells you which one of these is www.google.com. That's a hierarchical database, where each one of them contains just part of the information, and you often have to make several queries of different locations to find what you need. Object-oriented databases combine data and functions in an object-oriented framework, object database management systems. And database integrity checks to make sure that the data is obeying certain rules. So two users, for example, might try to change the same record simultaneously. So I used to work at a call center with like 100 people answering phones, getting calls from customers trying to update data, and they could easily try to change like one customer's address. So if two people try to change the same record, then the management system will prevent that. So when you put in type in new information and you press enter, it will now try to commit the update, and it will see, am I able to change that record right now? It might be able to, or that record might be locked because somebody else is editing it. If it's locked, then it can roll back and avoid corrupting the database by putting in half of one update and half of another. It either puts in one or the other, and the other one fails. And it keeps a journal to log all this so you can figure out what happened. Then you have, as I mentioned, you probably need more than one copy of your database for high availability. So you can have multiple servers, multiple copies of it, replication of your database, and a shadow database. There are various ways to do this. So you have extra copies of it on various devices so you can withstand faults. Then there's data warehouses where you store huge amounts of data. People call them data lakes sometimes these days, and data mining. This is a big issue. People have huge pools of data in which you can hunt for things. For example, the U.S. government in Utah has a gigantic server farm where they're recording all the data they're taking from the phone network and the internet, just years of it, incredible amounts of data, and somewhere in there is everything about every terrorist and kidnapping and financial crime and everything, and they're always trying to dig through there and find it. That's data mining, trying to find the good stuff in some gigantic pile of data. All right, so object-oriented programming, you got a series of connected objects, things like Java, C++, Ruby. So objects have data and methods, and this provides data hiding. You can have an object, and you don't see the internal structure from the outside. This is also called encapsulation, so you can use high-level abstract objects instead of referring to what's inside there. So you have objects. The objects have methods, which are active things, like functions that can apply on the object. They can send messages from one object to another. An object can be a child of another object, and then it will inherit the attributes and methods from the parent object. An object can receive a request which it cannot handle and then delegate, passing it on to a different object that will process it. And you can have polymorphism and polyinstantiation. We'll talk about it a little later. So here's so consider an object called addE that can add numbers. So if you give it two inputs of numbers, it can add them and give the output of 3. All right, that's an object here. But if this has the property of delegation, that if you give it something it doesn't know how to do, like subtraction, it will detect that and delegate it to another thing that can do the subtraction. If it's polymorphic, then it can actually have multiple kinds of inputs. It might take numbers and add them. If you give it text, it will figure out some way to add them too. So it actually has multiple functions, and it determines what it's going to do based on the input. They also call that overloading in functions in things like C++. Then polyinstantiation is where you have multiple records. This is how you deal with security levels in a database. So if you have an input for top secret data that's authorized, it'll give you the top secret output. But if you send the same input without the top secret clearance, you'll get different output. Like you might be querying something like a phone directory or a profile of people directory, a profile of employees. And if you aren't cleared for this, you'll only see the low clearance information. But if you're cleared for top secret, you'll see the whole story. And so polyinstantiation will take the same input request and determine what your output should be based on your clearance. Object request brokers are middleware to connect programs to other programs. And common ones are COM, DCOM, and Corba. So Microsoft made COM and DCOM, Component Object Model and Distributed Component Object Model, and this lets you have objects written in different languages to communicate with each other. So you can now build your program like a Lego thing, but just taking this component and that component and plugging them together. You can include things written in different languages, and it's supposed to be being replaced by Microsoft.NET. Corba is the open source version of the same thing, not the Microsoft proprietary one. Objects can communicate and via interface description languages, files that specify how the output from one object should be structured to feed into the next object. So object-oriented analysis analyzes the domain and identifies all the objects and their interactions, and object-oriented design then develops a solution. So you might have something like this. You have a network, then you have a tap to go to the sniffer so it copies all the data. Then you have this PCAP data, which goes to an analysis object, which analyzes it for various types of attack, and then it goes to an alerting object, which will send various types of alerts. So it's just a way to break up a programming job into chunks so you can program each component separately. And this is what in the news they said is true of that Russian malware called Ouroboros or Snake. They said it was very well designed by professional development. They professionally broke it up into logical chunks so they can keep updating the individual chunks, and each chunk only does one limited job. This is the right way to write a complex structure. So, let's try another Kahoot. 8B. All right. Cake. Let them eat cake. All right. Okay, which attack combines many low privilege records to deduce high privilege data? That's aggregation. All right. And which process removes redundant data? That's normalization. All right. Which concept allows a component to recognize input it can't handle and pass it on to a different component? That's delegation. Good. All right. All right. Which one is open source and vendor neutral? That's Corba. The other three are all from Microsoft. All right. 2. Damien's run twice. Good. Okay. So it is 10 minutes to 7. Let's take a break till 7, and then we'll do the last section. So I'm going to stop this recording.